Introduction to Quantum Information Processing. Hello, I'm Richard Cleve. I'm a professor at the Institute for Quantum Computing and the Cheriton School of Computer Science at the University of Waterloo. This is an overview of the course Introduction to Quantum Information Processing, which is cross-listed with these 6 different course numberings. The goal of the course is to provide a general overview of the field of quantum information processing, which includes quantum computing. The intended audience is primarily graduate students in computer science, combinatorics and optimization, applied math, pure math, and physics. But other people may take the course. In some cases, permission of the instructor is required. To take this course, you must have a basic understanding of linear algebra and probability theory. Here at Waterloo, it would be the content of these courses. The content of this course can be viewed as consisting of 4 parts. The first part, a primer for beginners, introduces the quantum information framework and is intended to ensure that the diverse group of students are all on the same page. The second part is on quantum algorithms and includes Shor's famous factoring algorithm and Grover's search algorithm. The third part, quantum information theory, includes a number of topics about useful mathematical formalisms for describing quantum states and the operations that can be performed on them, methods for encoding quantum states for the purposes of compression and for error correction, and the notion of non-locality, which is some strange behaviors that can occur when 2 or more physically separated quantum systems are entangled with each other. The fourth part of the course is about quantum cryptography and will include a description of the BB84 key exchange protocol. We'll now spend a few minutes giving you a brief glimpse of what quantum information is like. To understand quantum information, let's briefly review what conventional or classical information is like. If there are random processes, then the resulting state of a system can be described by a probability distribution. Of course, probabilities are greater than or equal to 0, and they sum to 1. Here's a simple example where there are 3 possible outcomes. The set of all probability vectors plotted in 3 dimensions is this triangular region. In higher dimensions, the corresponding region is called a simplex. If we observe the outcome, then we see a definite value. It's no longer a probability distribution. An equivalent way of saying this is that the state becomes a special probability distribution where one of the probabilities is 1 and all the other probabilities are 0. Okay, that's what classical information is like in a nutshell. For quantum information, the states are described by amplitudes rather than probabilities. Amplitudes can be negative. In fact, they can be complex numbers. The only condition is that the absolute values squared of the amplitudes sum to 1. So an amplitude vector is a vector whose length is 1. For a 3-state system, if we plot all the possible amplitude vectors, we get the surface of a sphere. All points whose distance from the origin is 1. We cannot directly see the amplitude vector of a quantum system. If we want to see something, we can apply a measurement operation which has the effect of turning the state into a probability distribution with probabilities the absolute values of the amplitudes squared. Then we can observe from this probability distribution. There's another type of operation that we can perform on a quantum system, a rotation. Note that if we rotate a vector of length 1, we get another vector whose length is still 1. If we do a rotation before measuring, then this effectively changes the coordinate system in which the measurement is performed, so the amplitudes can be different. This enables us to extract information from quantum states in interesting ways. The so-called quantum interference effects can be understood as changes in coordinate system before measurements are made. It gets interesting, especially when we have several quantum bits. Just as for a classical n-bit system, there are 2 to the n states, and the probability distributions are 2 to the n dimensional vectors. For n quantum bit systems, the amplitude vectors are 2 to the n dimensional. For the problem of factoring an n-bit integer into primes, the best conventional algorithm known scales exponentially, that is, exponentially in the cube root of n. But on a quantum computer, that is, a computer that manipulates quantum bits, there is an algorithm that scales polynomially. Roughly, it's quadratic scaling. Since several crypto systems are based on the assumed difficulty of factoring, a practical quantum computer would impact cryptography in a significant way. This is one interesting example of an algorithmic application of quantum information processing. There are other interesting things that can be done with quantum information. In addition to other algorithms, there are novel ways of achieving security in cryptographic protocols. Finally, I'd like to point out that the framework of quantum information has a very rich and intriguing structure. It can be viewed as a generalization of probability theory. Please feel free to look at the course website. You are welcome to view the lectures whether or not you're registered in the course. Thank you for your attention.